So we are looking at chapter 3, kinematics in 2 dimensions. And so 2 dimensions is going to combine what we've done in the last chapter, motion moving horizontally and vertically. So here we're going to use all of the same equations, but we're looking in the x direction and the y direction. So if we look at this example, we've got a cannon shooting a cannonball across the air. And so if there was a table or something here, that cannonball is going to continually go at the same speed. We're neglecting friction, so nothing's there to cause it to speed up or slow down. So you can see the intervals here are showing maybe a second. And so the distance between those are all the same because it's going at the same speed. It's not slowing up or slowing down. If we look at the next slide now, here we're taking into account looking at something falling. So if they were to just drop that cannonball straight down, now we're looking at the fact that gravity plays a role in things that are falling. But we know that a cannonball isn't going to just do one of these directions. It's actually going to be combined in the direction that it flows. So after 1 second, if we go this way, we're here. But if we go down, we're here. After 2 seconds, we're here and we're here. So it's technically going to be out here. After 3 seconds, that cannonball will be there. And after 4 seconds. So that's going to make the curved path that a cannonball actually would fly in. So we can see that in this next slide. So we can see that if we look at the arrows, the arrow for the horizontal component is staying the same length. And you can look at the velocity in the x direction at the bottom. It's always 100 meters per second. It's not speeding up or slowing down in the horizontal or the x direction. But as it falls, we know that gravity is causing it to accelerate or speed up as it falls. So in the y direction, you can see that arrow is getting bigger as it falls, and the Vy is increasing. So if we look, and this is kind of what I drew out earlier, we can see in the horizontal direction, the distance between the actual place that the ball is located is the same. But the distance that it's dropping is increasing because it's speeding up. We are going to be using the exact same equations that we've used, but now we're going to put them in terms of x direction and y direction, or horizontal and vertical. So x, just like an x and y chart in math, x is going to be your horizontal, y will be your vertical. So instead of using d for distance or displacement, we're going to be using x and y. Time is going to be the same. It's not going to matter if we're in the x direction or the y direction. Time will just be time. Acceleration, we're going to use a sub x and a sub y, depending on which direction we're talking about. And the same thing for our VI and VF. Now they're going to have VIX and VIY, and VFX and VFY. So if you're a person that needs to see those equations in terms of x and y, you can copy these down, rewrite them, pause the video. Or if you can just use your old ones and just remember this can be used for x, this can be used for y, you may not have to copy them down. But again, they're the exact same. So if we look at this and plug in some numbers, in the x direction, Vx, the velocity, there's nothing causing it to speed up or slow down. which means acceleration in the x direction is going to be 0. There's none. But if we are looking at the y direction, we're speeding up by 9.8, or by gravity every time. So a in the y direction is our 9.8 that we are used to from the last chapter. In the cannonball, they were just shooting that off of the cliff. Here, we've got this little guy is throwing it up in a curved path. So a couple things that we need to look at. If the ball is really traveling, it's going to travel basically in an arch like that. So when we look at the x and y components at each location, the actual path that it's traveling, if we move this guy over to here, it's making a triangle. So at each point that ball is along the way, we're making a new triangle with the x and y components at that specific instance. Now, when you get in college, if you have to take university physics, they will use calculus to determine the limits of all that and figure exactly what that is at each point. We aren't going to get that complicated. But another thing to notice, just like in the last chapter, when you throw things up, here it's 19.6 going up, and then it's slowing down to 9.8. And then at the very top, the velocity in the y direction is 0. And then we're going to come back down, so we're going to speed up again, 9.8, 19.6. And one thing to also note is that if we're the exact same height, so here and here are the exact same height, our velocities are going to be the same amount. Now, the only difference would be the sign, but that's going to just be indicating our direction. So then if we look up here at the same spot, 9.8, 9.8. So if we look at this, we're going to kind of work out a little problem here. It says the diagram shows the trajectory, and trajectory just means the path of a projectile, or the path of whatever object's flying through the air, is launched from non-horizontally from an elevated position on top of a cliff. So basically, we've got a cliff right here. The initial horizontal and vertical components of the velocity are 8 meters per second and 19.6 meters per second, respectively. So if we write that down, it's telling us that we've got velocity in the x is 8 meters per second. That's initial. And initial in the y is 19.6 meters per second. Positions of the object are at 1 second intervals and are shown. So between each ball that is shown is 1 additional second. Determine the horizontal and vertical velocities at each instant shown in the diagram. So we said earlier that acceleration in the x direction is 0. So it's not going to be speeding up in the x direction at all. So we can come through and say Vx is that 8. Here, Vx is 8. At this spot, Vx is 8. And all the way through. So now the trickier part comes in when we're looking at velocity in the y direction. But now we're just going to go back to what we've done last time. So we know that it's going to slow down 9.8 meters per second every second. So if we're starting at 19.6 at this initial spot, 1 second later, if we take the 19.6 and subtract 9.8, now at this spot, it's going up with a velocity in the y direction of 9.8. Now at the top, if we take the 9.8 here, subtract 9.8, now we said earlier at the top, the Vy is 0, and that checks out. 9.8 minus 9.8 up at the top is 0. Now it's coming back down. So now we're going to have to add 9.8. So 0 plus 9.8. So Vy at this point is 9.8. 9.8 plus another 9.8 is going to put this Vy back at the 19.6. And we can check that because those are straight across from each other at equal height. Now t is 5. Add another 9.8. So this Vy is 29.4. And then down here at 6, this Vy, add another 9.8, and we get 39.2. And we could even, see if it goes farther and farther down, keep adding those 9.8s. But we can look and see the velocity in the x and y at every single one of these points. You might be asked to find resultant velocities. So if you're given the Vx and the Vy, and you want to find the resultant of that, which looks like this nice little equation, but really what they're asking you is if Vx is a certain amount, and then maybe they're going a velocity in this direction, a certain amount, what's the resultant? And a resultant always means find the hypotenuse. So we're going to do Pythagorean theorem for that. If they ask for direction, you would have your triangle that you just solved. So for the Vx, Vy, that was your resultant. And what angle is it flying through? You would be solving for that angle. And you would use your sine, cosine, tangent, whatever sides of the triangle you happen to have. So if we look at this, a water balloon is launched with a speed of 40 meters per second at an angle of 60 degrees with the horizontal. Find the initial velocity in the x and y directions. Again, always draw out your pictures so you know what you're doing. There's the ground, there's our horizontal. We're launching water balloons. So the water balloons are going to fly out like this. So their initial launch is going to be with a speed of 40 meters per second at an angle of 60 degrees. We want to solve for velocity in the x and velocity in the y that they're trying to solve for. So this is just going to be a sine, cosine, tangent problem. Over here, Vy is going to be 40 sine 60. And Vx, since we're dealing with this angle, it's going to be 40 cosine 60. And you can plug those in and see what they happen to be. So we've got 40 sine 60 gives me 34.6 meters per second. And 40 cosine 60 gives me 20 meters per second. On this problem, we have a lot going on. We've got a motorcycle stunt person traveling at 70 miles per hour, jumps off a ramp at an angle of 35 degrees to the horizontal. How high and how far are they going to travel before they land? Also, how long would they be in the air? So if we have this motorcycle stunt person, he's going to start over here, jump off that ramp, fly through the air, and land. It says he's starting at 70 miles per hour, which we already know we don't like that. We're going to have to put it in meters per second. And the angle is 35 degrees. It's asking how high is he going to be going in the air. So at this top point, how high is that? What is this distance, or now we're calling this y? And how far is he going to travel? So from here, we want to know the distance to where he's going to land. And so that's actually going to be a distance in the x direction. Now, if you guys want, we can say dx, and we could say up here dy. Either one, whatever's easier for you guys. And then they also want to know how long would he be in the air. So kind of like last chapter, we had to figure out how long is it to the top and then double that because he's got to come back down. So we've got a lot going on here. The first thing we need to do is change that 70 miles per hour to meters per second. So we need miles into feet, 5,280 feet. And if you guys can cut out some of these steps, that's fine, but we're going to go ahead and work it out. So feet into inches, 12 inches, 1 foot. Inches, 1 inch is 2.54 centimeters. And then we've got 100 centimeters is equal to 1 meter. So that takes care of the miles and meters. And now we got to get hours into seconds. So since hours on the bottom, now it's going to be on the top. Seconds on the bottom, so 3,600 seconds in 1 hour. So if we use our calculator, now we're going to take 70 times 5,280 times 12 times 2.54 divided by 100 divided by 3,600. And that gives me 31.29 meters per second. So we write that over here, 31.29 meters per second. I'm going to erase all this because we are going to need the room. The first thing that I need to do is find the initial velocity in the x and y direction, which means I'm going to have to make a triangle out of this. So we have the hypotenuse, which is instead of the 70 is now the 31.29 meters per second. We've got an angle, so now we can solve for the x initial and the y initial. And we're going to use sine, cosine, tangent. So I'm going to bring that over here just to make it a little bit easier to see. So this is 31.29 meters per second. This is 35. So Vx initial is going to be 31.29, and this is cosine of 35. So if we type that in, 31.29 cosine 35, we get 25.63 meters per second. Then velocity initial for the y is going to be the 31.29 sine of 35. So if we plug that in, we get 17.95 meters per second. Now, if your rounding is a little bit different than mine, that's fine. Maybe you have 17.94, 17.96. As long as you're close, you're on the right path. So I'm going to write those over here just so we can kind of keep things a little bit more organized. So velocity in the x direction initially, we've got 25.63 meters per second. And then the y, VIY, 17.95 meters per second. So I'm going to erase this. Now the first part of our question, how high did it go? So we're basically looking, how high up did it go? So that's really just the y direction. Because remember, even though we said this is Vxi, in the x direction, we're not speeding up and slowing down. So we can really just say this is the Vx. So when we were using our equations from the last chapter to find out how high something went, we said the top is 0. So Vf is 0. And again, we're working in the y direction. So we know Viy is 17.95. Vfy is 0. Acceleration going up and down is 9.8. But we're going up, so things are going to slow down. And we're looking for how high does it go? So we're looking for distance in the y direction. So if we're looking at our equations, we're going to be using Vf squared equals Vi squared plus 2AD, because we don't have a time right now. And so I put Vfy and Viy in there because we're just looking in the y direction. So this is 0. This we said was that 17.95 plus 2, negative 9.8, and we're solving for D. So we're going to square that 17.95 and subtract it over to the other side. So that gives me negative 322.2, and that equals my 2 times my negative 9.8 gives me negative 19.6 D. So if I divide each side by negative 19.6, my distance is going to be 16.44 meters, and that's in the y direction. So that's how high it's going to go. So we've solved the first part, so I'm going to put that up here. Dy equals 16.44. Now we need to know how far did it go. Well, to know how far it goes, we really need to know how long it's going to be in the air total, because how far it goes is going to be dependent on the Vx. And so since we aren't accelerating, Vx is going to equal dx over t. And you can write on your equation sheet this equation. And for all of those that we saw earlier in the notes that were the old equation with the x's plugged in, you can probably maybe put a pencil x over it, because most of the time you will not be using those equations in the x direction because we're not going to be speeding up or slowing down. So right now, if we're finding dx, we have Vx, but we need time. So we need to know how long this guy's in the air. So if it is going up in the air, we can use the y information to find out how long it's going to take to go up. And then we can double it to find out how long it's going to take to go down. Because if it's following this path, however long it takes it to get to the top, it's going to take it to get back to the ground. And the time is not going to be different for how long it takes it to get to here and here compared to here versus here. Because the time is what connects the x and the y directions. So we can find the time to the top and then the total time in the y, and then use that time for the x. So we've got all kinds of y information. So we could just say Vfy equals Viy plus AT, because that's the easiest one to use. So VFY we said was 0, and VIY was the 17.95. And acceleration in the y direction is our 9.8, and we're going up, so it's negative, and so we're solving for t. So we're just going to do 17.95 divided by 9.8, and the time is 1.8 seconds. That's just to get to the top. So to get to the top and get back down, we're going to multiply that by t, or by 2. So total time is going to be 3.6 seconds. And so that answers that last question. How long is it going to be in the air? So I'm going to say t, I'm just going to put t sub t for total time, 3.6 seconds. Now we can go back and solve for how far it's going to go. So we're going to use that Ex equals dx over t. So we said Vx was the 25.63. Dx is what we're looking for. And when we're looking for dx, we want to use that total time because we're looking for this distance here rather than just to the top. So 3.6 seconds is what we're going to use. So 25.63 times 3.6 is going to give me a dx of 92.27 meters. So there's one answer. And there are other two answers for this one problem. Let's look at the next one. All right, so the last one was an arch problem. And this one is what I call a cliff problem. There's basically two types of problems in this chapter. It's either an arch or it's a cliff. So here we have a pool ball leaves a 0.6 meter high table with an initial horizontal velocity of 2.4 meters per second. Predict the time required for the pool ball to fall to the ground and the horizontal distance between the table's edge and the ball's landing location. So I'm going to show you what I mean by a cliff problem. So basically, it's like we're dropping something off a cliff, but here we're dropping it off of a pool table. So you've got the pool ball, and it's going to fall and go like that. So we know how high this table is. It says it's 0.6 meters, and so that's our distance in the y direction. And then it says the table leaves with an initial horizontal velocity, which is really cute because we know that the horizontal velocity doesn't change, so we don't need to worry about saying initial or final. So Vx is 2.4 meters per second. Predict the time required for the pool ball to fall to the ground and the horizontal distance between the table's edge, which is here, and where it's going to land over here. So this is dx that we're looking for. All right, so if we look at this, we have to basically do two steps. We have to figure out the time, and that's going to connect, like I said, the y and the x. So if I know dy, we can go back to the equation in the y direction. Initial y, when we're dropping something, and if this was out here, and we just held it and dropped it down, my VIY is going to be 0. So we can use that same piece of information. So then we know dy is 0.6. We know acceleration, falling, is 9.8. We're trying to find t. So we can use a d equals VIT plus 1/2 AT squared. VI 0, so that's going to go away. So most of the time here in these cliff problems, we're going to use dy equals 1/2 ay, which is 9.8 t squared. So we've got 0.6 equals 1/2 9.8 t squared. And so I'm going to solve for t. So t, 0.6 divided by 1/2 divided by 9.8. Then I'm going to get my square root. And so my time to fall down to the ground is 0.35 seconds. So that answers the time required. So I'm going to put that up where I can save it. Time is 0.35. And then the other question we wanted to know was the dx. And so if you remember what I said last problem, in the x direction, all we have to use is dx equals dx over t. We have our bx, which is the 2.4. We're looking for dx, and we just solve for t at 0.35 seconds. So we're going to multiply and find that dx is 0.35 times 2.4, and we get 0.84 meters. So there's one part of the answer, and there's the other part. Cliff problems, a little easier than the arch problems. So really, in these type of problems, they're either going to give you the dy, and you use the dy equals 1/2 at squared to find time, or they're going to give you the dx and then the vx, and you can use this equation to find time, and then plug it back in this one to find the dy. So those two equations right here are going to what you're going to need for these cliff problems. Let's see what else we've got. Soccer ball is kicked horizontally off of a 22-meter high hill and lands a distance of 0.35 meters from the edge of the hill. Determine the initial horizontal velocity of the soccer ball. First, we need to determine, is this a cliff or is this an arch? We're kicking it off of a hill, so this one is going to be a cliff, so it's a lot easier. So here's the soccer ball. It's kicking off, and it's going to fly that way. And it says it's kicked horizontally off of a 22-meter high hill. So 22 meters high tells us our dy lands 35 meters from the edge. So that's our dx. Dx equals 35 meters. We want to know the initial horizontal velocity of the soccer ball. So if we write down those two equations from earlier, so we said Vx equals dx over t, and we've also got dy equals 1/2 at squared. These are what we're going to use. So we'll plug in what we do know already. We're looking for this ultimately. So Vx equals, we know dx is 35. We don't know t yet. We know dy is 22. So we've got 22 equals 1/2. A is 9.8 t squared. So if we look at these two side by side, what I need to solve for first is time here. Then I can plug it right back in there and solve for my Vx. So if I solve the t, I've got 22 divided by 0.5 divided by 9.8. Square root that. T turns out to be 2.1 seconds. Then I'm going to plug that back over here. So instead of t, now I've got 2.1. So Vx is going to be my 35 divided by my 2.1, 16.7 meters per second. And that's my answer. We will do many more of these. So remember, for the cliff problems, you're going to use these two equations here. And I might even write down cliff and then these two. And then the arch, we're going to have lots of different equations.